This week, we bring you news of the sharpest black hole merger we have ever heard. And from this merger, scientists may just be able to confirm Stephen Hawking's bold area law, which says that the area of a black hole horizon can never decrease. On March 2022, at about 8:45 a.m. Eastern Time, LIGO and Virgo's detectors registered a signal that started out as a chirp and ended with a weird sort of death rattle. Ew. It was the first time in LIGO's history that they captured both parts of the orca-esque cry clearly enough to say, yes, it's definitely an orca. This cry contained information about the two merging black holes and their spins, and it matched very well with the theoretical prediction of what a merger should sound like. The signal had a high SNR of 31. SNR stands for signal-to-noise ratio and tells you how many times the signal H bigger than the noise. A rough rule of thumb is that an SNR of 5 is considered good, so this event was exceptional. This merger was remarkable also because of the death rattle. It is known as the post-merger ringdown and is a direct probe of what happens when a black hole forms after the merger. The newly formed black hole vibrates or rings down to its new size and settles into a state of no net linear momentum. During this phase, the black hole emits gravitational waves at a range of frequencies. This part of the waveform is extremely weak and hard to detect, but it contains a wealth of information about the properties of the final black hole. In this case, they could check Hawking's famous area law, which says that the surface area of a black hole cannot decrease. Technically, the law is about the area of the event horizon and not the size of the black hole. But since the size of the event horizon is proportional to the mass of the black hole, the same thing more or less. Hawking originally derived his area law in 1972, and it is one of the pillars of modern black hole physics. It has been checked many times, but never before with anything close to the accuracy that LIGO can provide. You see, in any merger, the total event horizon area can't go down, like an entropy for black holes. To understand how LIGO can measure this, let's look at a very simple example. Consider a black hole of mass m in 2 dimensions. Its Schwarzschild radius and hence the area of its horizon is proportional to m. Now, imagine a second black hole of mass m coming up to it. As it falls towards the first black hole, their horizons merge, creating a bigger black hole with horizon area 2 meters. If the two black holes had the opposite angular momentum, the final black hole would still have the same mass, but its horizon area would be a bit bigger than 2 meters because some of the kinetic energy gets converted into the gravitational energy of the horizon. The area can increase, but it can never decrease. To see how LIGO measures this, let's briefly recap how interferometers work. The LIGO detectors look like giant arms that are a few kilometers long and move laser beams back and forth along those arms. They measure the strain, meaning the change in length of the arms caused by gravitational waves. When you do this for long enough, you can measure tiny changes in length down to 10 to the minus 21st power. You do this by splitting the beam into 2 parts, making them interfere. If they come back with the same phase, the path length difference was a multiple of the wavelength, so it canceled out. But if they come back with opposite phases, the path length difference was half a multiple of the wavelength, so it added up. By comparing the two, you can figure out how much the arm changed in length. That's why the ringdown is so important. It is a unique feature of black hole mergers, and it makes it easier to extract information about the masses and spins of the merged black hole. Also, it is a smoking gun that tells us we're dealing with a real black hole merger. With the data from this merger, they could check that the results agree with a Kerr black hole, a black hole with a non-zero spin, and they confirm that the area does not decrease. Hawking's area law is a remarkable theorem. It is a unique feature of gravity in 4 dimensions, has profound implications for our understanding of black holes, and it tells us something about the nature of space-time. This new result reinforces the predictions of Einstein's general relativity and Hawking's theorem. It gives us improved estimates of the masses and spins of the black holes involved, and it sets the stage for the next generation of what gravitational wave detectors like Cosmic Explorer ET and LIGO India. Of course, this is just one event. We need more events to confirm this result. We need to see that the results are consistent between different detectors. And we need to keep checking that the results agree with Einstein's theory. But overall, this result looks great. Do you buy the area never shrinks idea? Comment below. And don't forget to subscribe for the next wave. The research was published in Physical Review Letters. Thanks for watching. Special thanks to our supporters who make these videos possible. And thanks to you for watching.